Hey everyone, in this section we're going to deal with a topic called thermodynamics. We're going to talk about the way the engine breathes and operates and get you a sense for how efficient a typical internal combustion engine is. So this is actually a pretty short topic. Think about what's happening inside the engine for a minute while it's running. This little animation shows that we've got some, the left side is our intake port and the right side is our exhaust port. And if you could hook a pressure gauge up, just like a tire pressure gauge but with higher capacity, up to what's inside that cylinder, what you'd notice is the pressure of those burning gases on the inside of your engine would always be changing. On the intake stroke, you actually have a little bit of vacuum or negative pressure, and then it goes up on the compression stroke. That's going to raise the pressure up. Then the fuel ignites, and that makes the pressure go up even higher. And then our exhaust valve opens, and our pressure drops way down because we can push all that exhaust out. And then, of course, it all starts over again. We'd start out with an intake where we have vacuum, pressure goes up, then pressure goes way up, and then it drops down again. I don't want to get too carried away with the technical aspect of this, but there's an important fact from that I want you to understand. So if you take a look at this diagram, what this means is that if you were to track the pressure, which is what the left side of this graph does, it keeps track of engine pressure inside the cylinder while the engine is going back and forth from top dead center down to bottom dead center. So let's start on our intake stroke. If we start out at top dead center on the intake stroke, the pressure is zero, and in fact it's a little bit negative, but our intake stroke, we have zero pressure in that cylinder when we go from top dead center down to bottom dead center. Okay, there's no pressure at all there. But then the intake valve closes and the piston starts going back up on the compression stroke. And as it gets up to top dead center, the pressure inside the cylinder, that's what you're checking when you do a compression test, is maybe 200, maybe 300 psi, somewhere in here. Okay, and that, of course, that better be the same around all cylinders. That's what you do when you're doing a compression test. But hopefully when you're doing a compression test, the engine doesn't actually start. If it did, that burning fuel would suddenly heat up and expand, and you get this great big spike in pressure, 300, 400, 500, 600, 700, if it's turbocharged, even higher, 800, maybe 1,000 psi. And all that pressure then pushes down on your piston. So you get this really, really high pressure, and the only thing that lets that pressure go is the fact that the piston starts moving down. As the piston starts moving down, then the pressure in the cylinder starts to drop. Then when you get to bottom dead center, there's still a little bit of pressure because there's still fuel burning, but your exhaust valve opens and your pressure drops back down to zero, and your piston pushes that exhaust out. And this happens, 2,000 times per minute, 2,000 revolutions per minute. Well, half of that, since only every other. And this happens about 2,000 or 3,000 times per minute, once with every revolution. We compress and get some pressure. We ignite the fuel. That causes the cylinder pressure to go way up. The piston starts going down. That starts easing our pressure. And then our exhaust and intake strokes, we have virtually no pressure because the valves are open. Okay? But here's the thing. If you could average all that out, if you could take the times where there's no pressure in the cylinder and average it out with the times when there's a lot of pressure because the fuel is burning, you get what I have shown here in purple. And this is your average pressure inside the cylinder. Sometimes it's higher, sometimes it's lower. It's the average. And you might remember from math you've had before, we haven't dealt with this term, but we call the average in mathematics, we often call that the mean. Okay, that's the pressure that actually makes the engine run. If there's no pressure pushing on the piston, engine ain't gonna run. So we call that pressure the mean or average effective, that means it's doing the work, pressure, or we're going to abbreviate that with MEP, the mean effective pressure. Every engine has some mean effective pressure, and it's a few hundred psi. Turbocharged engines have a higher mean effective pressure. They operate under higher pressures. Same thing with supercharged engines. If you've got a really dirty or clogged up air filter, then your mean effective pressure goes down. Your engine doesn't operate with as much pressure, and that's why you lose fuel economy when you have a dirty air filter. So this pressure is the biggest factor in how much power your engine produces. The more pressure you have, the more power you get out of the engine. That's what every engine builder is trying to do. More fuel, more oxygen, more pressure. And that ultimately is what makes the torque on the crankshaft. The theoretical torque, that is to say the amount of torque that we should get out of that engine, is generated by the mean effective pressure, and we can figure this out by calculation. But what's the other thing that will affect how much torque there is on the crankshaft? Well, certainly it is the throw. That is to say how long the crank is or how long our lever arm is on our crankshaft. That certainly affects how much torque we get out. And in fact, the piston size does as well. The bigger the piston, the more space there is catching that pressure. We saw that in our force pressure area relationship. But if you multiply the length of your lever, that is to say your stroke, technically it's half the stroke, but we're going to kind of ignore that for now. If you multiply that stroke of your crankshaft by the piston size, you get the displacement. So really there are two factors that determine how much torque comes out of an engine. And what factors are they? They are the mean effective pressure and the lever and piston size combining, which is your displacement. So surprisingly, if you know the average pressure and you know the size of the engine, you can calculate how much torque you should get out of the engine. And here's how. Here's a formula for your sheet, and one of our last ones actually. We're getting right down to the end here. We've only got a couple formulas left. The indicated torque, and again I want to emphasize what indicated means. The indicated torque is the theoretical, it's the theoretical amount of torque that you should get out of an engine. It's not what you actually get out if you put it on a dynamometer. It's the theoretical amount, the mathematical amount of torque, that is. That is found by this simple formula. You take your pressure, MEP, times the displacement of the engine, that needs to be in cubic inches, and you divide by 150.8. That's it. It's that simple. Let's do an example. Okay, Chrysler 360 cubic inch engine operates with a mean effective pressure, that is your MEP, of 195 psi. That means that on average, when that engine's running, those pressures have about 195 psi in them, sometimes more, sometimes less. That's at 3,700 RPM. If we rev the engine differently, then this would change. Okay, let's calculate how much indicated torque we have. Okay, well our formula above says our indicated torque is our MEP times displacement divided by 150.8. So that means we're going to take an MEP of 195 times a displacement of 360 and divide it by 150.8. And that gives you, if you type that into your calculator, about 466. Now 466 what? What are the units on that? Well, what did we found? We just found a torque value, and so those would be foot-pounds. And that's all there is to it. Now, here's the thing. That's not how much torque the engine will actually make, and we'll talk about why in a minute, but this is how much it could make based on the amount of fuel that it's taking in. Now, we can use that to figure out what the indicated horsepower is. Again, the indicated horsepower is the theoretic. That is to say, it's how much horsepower the engine could or should make. And we can build that based on our indicated torque formula. Here's how. Okay, we need a fact from earlier on in the course here. To find our indicated horsepower, we're going to take our torque. That is to say, our MEP times displacement divided by 150.8. Now, do you remember how we find horsepower if we know the torque? This is our torque right here. You might remember that we multiply that by the RPM, and then you divide by, yeah, I know you just said it in your head, 5252. So we can combine these two bottom numbers, the 150.8 that we had from our indicated torque formula and the 5252 that we used to change that into horsepower. We can combine those, and if you do that, you get this new formula. Don't write this one down yet. We're going to change it one more time. If we take our MEP times our displacement times our RPM, and then if we take 150.8 times 5252, you get 792,001.6. Well, we're going to round this off and ignore that 1.6, and that gives us a formula for indicated horsepower. This is the formula you should write on your sheet. To find our indicated horsepower, you take your pressure times displacement, just like you did for torque, but you also multiply it by your RPM, because remember, horsepower depends on RPM, and then you divide by 792,000 instead of 150.8. So there you go. These are two of the three formulas you need for this topic, indicated torque and indicated horsepower. Make sure that you have those written down. And again, our displacement, just like with torque, has to be in cubic inches for all this work. Okay, I want you to do a practice problem. Pause the video and work this one out. A Buick 2.8 liter engine has an MEP value of 165 at 3,900 RPM. I want you to tell me what is the indicated horsepower. That's pretty straightforward, but notice that our displacement is in liters. You're going to need to convert that into cubic inches before you can use the formula that we just used. Go ahead and do that. Unpause the video to see if you get this one right. Okay, let's take a look. First of all, that 2.8 liter engine, we have to figure out how many cubic inches that is. You've done this before, just recently. 2.8 liters, we'll trade in liters for cc's and 16.39 cc's for every cubic inch. You should find that that is a 170.8 cubic inch engine. Okay, that's our displacement. Now, to find the indicated horsepower, you can use the formula that we just developed. We're going to take our pressure times our displacement times our RPM and divide it by 792,000. In our case, that's 165 psi. That was given to us, times 170.8, that's the displacement that we found, times our RPM of 3,900, that was given to us, divided by 792,000. Now, when you try typing this into your calculator, you could get an error message. This top number gets so big that it exceeds the memory on some calculators. So here's a trick. This is a fraction. Cancel off 2 zeros there and 2 zeros there. So you're going to enter in 165 times 170.8 times 39 and divide by 7920. You cancel off 2 zeros off the top and 2 off the bottom, and that keeps it small enough to fit in your calculator. Go ahead and do that. Type that in, and you should get 139. Now 139 what? What did we just find? We found not just the horsepower, but the indicated horsepower. We abbreviate that with IHP. And that tells us that that's not what we're actually getting out of the engine. That's how much theoretically is there. Why isn't this actually getting out of the engine? Let's talk about that for a minute. Before we go on, I just want you to make sure that you recognize that term, indicated. So that's the theoretical horsepower. That's not what you actually measure with a dynamometer. When you put an engine on a dynamometer, what you're measuring is what's called the brake values, because sometimes a dynamometer is called an engine brake. Okay, so here's the thing. Indicated torque and horsepower values are theoretical. That's what the computer says, or what the math says that the engine should make. The brake torque and horsepower are what you actually measure on a dynamometer. Which one of those is going to be higher? Yeah, hopefully you recognize that the indicated or theoretical horsepower is always going to be higher than what we actually measure on the dynamometer. Why? I'm going to give you one word on this. Why is the brake torque or brake horsepower always lower than the indicated torque or horsepower? One word. Friction. If the engine didn't lose any power internally, these two things would be the same. But we lose a lot of power internally, and that's what causes our brake value to be lower. It takes power, horsepower or torque, both. It takes power to turn the oil pump, to turn the camshaft, to turn the distributor, if there is one. It takes a lot of power to move the pistons up and down. There's a lot of friction in those rings. And there's engine bearings, right? Even the kind of motor oil you use, heavier motor oil uses more power. That's why the only oil that's branded as energy conserving are lighter weight oils like 1030 or however. You won't see energy conserving on 10W40 oil. It's thicker. It uses more power just to pump the oil. So here you go. Here's another formula for you. Indicated horsepower is what we start with. That's our theoretical amount that we calculate. If you take away the friction that we lose inside the engine for all these things, what you're left with is brake horsepower. Its frictional losses are kind of like tax. Frictional losses are the tax of doing business, of running, and what you're left with is the brake, and that's what you can actually use to power the vehicle. To figure out the indicated horsepower, we use that calculated number. We use a calculator to do that. But to get the brake horsepower, we use a dyno or a dynamometer. So these two things are related. Here's how. If you think about this as being a percent problem, which we're going to in a minute, our indicated horsepower, that's our base. That's what we start with. Then we lose some due to friction, and our brake horsepower, that's our amount. That's what we're left with. So mechanical efficiency is just the percentage that we actually get out of the engine. So we take our brake, the amount, and divide it by the indicated, which is the base, and that gives us our percent efficiency. So let's do a problem here. We've got a Honda 1.8 liter VTEC engine. It has a mean effective pressure at 210 psi at 5,600 RPM. A dynamometer measures 142 bhp. You know what B stands for now, right? You'll see that all over the place now that you know what it means. Some people think that means base horsepower. That means brake horsepower, as we've just seen. Engine dyno measures 142 brake horsepower. And so my question is, what is the mechanical efficiency? Well, we know what the brake horsepower is, so our mechanical efficiency is going to be our brake horsepower of 142 divided by the indicated. We got to figure out what that is. Now, here's the thing. This formula works either with horsepower or with torque, but you cannot mix or match them. If we're going to use horsepower, these both have to be horsepower. And if we're going to use torque, these both have to be torque. So what are we given here? We're given 142 brake horsepower. Therefore, we must use horsepower for this problem. So let's do that. Okay, so our mechanical efficiency is 142. We're going to use horsepower for this since we were given horsepower. 142 brake horsepower divided by the indicated horsepower. We got to figure out what our indicated horsepower is. And so our indicated horsepower, that's going to be found by taking our pressure times displacement times RPM divided by 792,000. Let's do that. Our pressure is 210 psi times our displacement. Oh, we got to figure out what the displacement of this engine is. 1.8 liter VTEC. 1 liter is 1,000 cc's. 16.39 cc's per cubic inch. And that 1.8 liter VTEC turns out to be 109.8 cubic inches. So our indicated horsepower is going to be our pressure of 210 psi times our displacement of 109.8 cubic inches times our RPM, 5,600 divided by 792,000. 210 times 109.8 times 5,600 divided by 792,000. Here again, type that into your calculator, but cancel off 2 of those zeros, and you should end up with 163. Now, what units are those? That's 163 indicated horsepower. And now we can do our calculation. This engine should make 163 horsepower. That's our indicated. But it actually only makes 142. That's what we measured at the dynamometer. That's our brake horsepower. And 142 divided by 163 turns out to be 87% mechanical efficiency. So the other 13% that we're losing is all going into heat, noise, and friction. It's doing other stuff that allows the engine to run. Okay, I want you to do this practice problem. A Ford 302 has an engine MEP of 180 at 4,800 RPM. Dynamometer measures the engine output at 315 foot-pounds of torque. What is the mechanical efficiency of this engine? Okay, I'm going to let you do that one, but I do just want to point out one thing. What was our brake value here? The dynamometer measures the engine output at 315 what? These are foot-pounds. And so here you're given the brake torque. So when you do this problem, you better use torque instead of horsepower. Go ahead and do that. Unpause when you're ready to see if you've got this one right. Okay, here we go. What is the mechanical efficiency of this engine? Our mechanical efficiency, remember, is the brake divided by indicated, and we can either use horsepower or torque, but we got to stick with one or the other. If you don't have this formula written down, by the way, this is your last formula. Make sure that this one goes on your sheet. That is the last formula for this topic. Okay, brake torque divided by indicated torque for our case. So our brake torque, dynamometer torque, is 315 foot-pounds. And now we need to figure out the indicated torque. How much should the engine be making? Indicated torque, you've got this one on your sheet, I hope. Pressure times displacement divided by 150.8. Here we're using torque since we were given a torque. MEP is 180. Our displacement, we don't need to convert this time. That's 302 divided by 150.8. And when you divide that, you get 360 foot-pounds of torque. That's what the engine should be making. That is our indicated torque. So that's in the bottom of our fraction. As always, the units cancel. That's the other reason they need to match. And 315 divided by 360 gives you 0.875, which we would call 87.5, or we could round that off and call it 88%. Notice that we never used the engine RPM, and that's okay. If we rev it to a different RPM, this efficiency might change, but only because our brake and indicated values would change. Okay, so to summarize everything that we've done, there's really two main facts that you need to have a good handle on. The first one is this, that the indicated torque or the indicated horsepower, that is to say our theoretical amount that the engine makes, can be found using these two formulas. These need to be on your sheet. Indicated torque, MEP times displacement divided by 150.8. And the IHP, indicated horsepower, is MEP times displacement times RPM divided by 792,000. Once you find that theoretical amount of torque or horsepower the engine can make, you can take the brake power or torque, which you would actually measure on a dynamometer, and divide it by what it should be making, and that gives you your mechanical efficiency for this engine. That is always going to be, by the way, less than 100%. And it's always less than 100% because the brake value will always be less than our indicated value. Okay, these problems will be posted in Blackboard, so go ahead and do this section and I'll watch for those problems.